A population of 500 bacteria is introduced into a culture and grows in number according to the following equation. P of t is equal to 500 times the quantity 1 plus 4t divided by 50 plus t squared, where t is measured in hours. Determine the rate at which the population is changing when t equals 2. So we are asked to determine a rate here. And remember, this is a rate of change, specifically at t equals 2. So this is asking for an instantaneous rate of change. And anytime we're determining a rate, an instantaneous rate of change, that means we're really computing a derivative. So we need to compute the derivative of p. In other words, we need to find p prime. Now, the function that we are given, if I rewrite it over here, p of t, you have two options. For some reason, a lot of my students want to distribute that 500, and you certainly could. There's nothing keeping you from distributing. But if you can also remember that this 500 is just a constant being multiplied by this quantity, so it's a constant multiple. And we know that when we're taking the derivative of a constant multiplied by a function, then we can really just bring the constant out in front and multiply it by the derivative of the function. So rather than distributing this in, I like to just treat the 500 as a constant multiple. And that means it's just going to be here multiplied by the derivative of what's inside the parentheses. So in the parentheses, we have two terms. We have the 1, and then we have the quotient, the 4t divided by 50 plus t squared. So starting with the 1, the derivative of 1, remember, the derivative of a constant alone is just 0. So derivative of 1 will be 0. But the derivative of the quotient, the 4t divided by 50 plus t squared, that's a quotient which requires the quotient rule. So we are going to use the quotient rule next. And we have the function in the numerator here, which is our 4t, and then the function in the denominator is the 50 plus t squared. So just a reminder again, when you're taking the derivative of a quotient, we need the quotient rule. I'm just going to jot it down over here. So if we have the derivative of f divided by g, our little memory trick for this, remember, is the low function, low d high, so low times the derivative of the high function, low d high, minus the function on top, high, times the derivative of the low, so we say high d low, all divided by the low function squared. So low d high minus high d low, square the bottom, and off we go. So we'll start with the low function, which is the 50 plus t squared. So that's low, times the derivative of the high, and the derivative of 4t is just 4. So there's low d high, minus, and I'm already realizing I do not have enough room, so let me pause. I'm going to erase. That's better. Okay, we have low d high minus high, which is the 4t, d low. Now the derivative of the 50 plus t squared, again 50 is a constant, so that's just 0, and the derivative of t squared is 2t. So that's low d high minus high d low, and then we square the bottom. So 50 plus t squared, the quantity squared. So this is going to be our derivative. So now at this point, you have two options. We need the rate of change at 2 hours. So you could go ahead and substitute in 2 right now if you wanted to. Or if you want to go ahead and do some simplifying, kind of clean this up a little bit, you could also do that. So it's really up to you. I am going to opt to clean it up a little bit. So I'm basically just going to distribute. So 50 times 4 is 200 plus 4t squared minus 8t squared, all divided by that quantity 50 plus t squared, the quantity squared. So now I have 500 times negative 4t squared plus 200, all divided by the quantity 50 plus t squared squared. So here is my simplified derivative. This is my rate of change at any time for this particular population. And now we want the rate of change change specifically at t equals 2, and t was measured in hours, so at 2 hours. So here's where you just grab out your graphing calculator and go ahead and substitute in 2 for t. Be super careful with parentheses and such on your graphing calculator, but if I round to 2 decimals, I'm getting an answer of 31.55. Now, let's think about units, and then we want to kind of write an answer, a summary sentence for our answer. Remember, when we're calculating this rate of change, then we're really calculating, in this case, the change in P over the change in T. Now, P was a population, and in this case, it was bacteria. So that means the change in P is going to be a measurement of bacteria, and T was time measured in hours, so that would give us a unit of bacteria per hour. And because we are getting a positive rate of change here, that tells me that the population of bacteria is growing. It's increasing. If we ended up getting a negative rate of change, then the population would be decreasing. So they would be dying off, or dying. In this case, they're not, they're increasing. So basically we can say the population is growing at a rate of 31.55 bacteria per hour at t equals 2 hours.